Alright, what we'll do is we'll go through step by step the problems 3, 4, and 5 on that sheet that I gave you involving inclined planes. And to take a look at number 3, you have a situation where we have an incline. The cart is on the incline. It's attached to a string that's tethered to the wall, and the cart is just not moving. So the mass of the cart, we're told, is 12 kilograms. The angle of the incline is 23 degrees, and I think that's about all we're given here. And we're told that it's at rest. So when we want to draw a diagram of all the forces acting on the cart, and your give me is always gravity, you got your force of gravity down like that. The fact that it's on a surface, your normal force perpendicular to the incline, and then the last force we have is the tension, and the tension has to be along the string itself. So there's the 3 forces, and they have to all cancel each other out. Not very easy to see here until we get into components. So when we look at the gravity, you're going to have FGY this way, and FGX always points along the surface of the incline. So we're looking at those 2 vectors in addition to the ones that we're going to leave alone, which is the normal force, which is that way, and the tension, which is this way. Now keep in mind here, when we're doing our coordinate system, it was initially like this, but then we rotated it so that it's like this. So we have positive and negative directions that we have to pay attention to here. And essentially, there's all our forces. If the cart is at rest, that tells us that the net force has to be equal to 0. And the reason that is because F net equals MA. And A is 0 here, because this thing is just not moving. So that means that F net is 0, which means that all your forces are completely balanced. Now, I know that these 2 are going to cancel each other out, and what I have to look at are these 2. These 2 have to also cancel each other out. So what I can also see is that FGX and tension, they have to be equal to each other. So if we did the net force in the X direction, we know it's 0, we can write an expression involving our net force in the X direction involving this vector and this vector here. T is in the positive direction here, so I'm going to make it positive. F of gx is in the negative direction, and then once we just look at this little equality here, if I move that over there, it becomes positive, and you get F of gx and t, they're equal to each other. So that explains to us mathematically that they are balanced out. Now we always have the ability to solve for FGX. FGX is equal to mg sine theta, where theta is the angle of the incline. So if I'm going to do the math here, I have a mass of 12, 9.81 for G, and then we have sine, the angle is 23. And what I'm getting is 12 times 9.81 times sine of 23, and a force of 46 newtons. Now that is FGX, but that also happens to be tension as well. It's just that you got 46 newtons pointed that way and 46 newtons pointed that way. So they do end up balancing out. So hopefully you see that we're doing a diagram and we're applying the second law, and that ends up being our approach that we want to take to pretty much all these problems. Next one, you see 2 kids on a sled, 100 total kilogram mass of everything. And our sled is like this, so it's basically an object that's just going down the incline like this. We're asked to draw the free body diagram, so that's going to be pretty easy. Your F of G is down, your normal force is that way, and I think right now we're told that it's frictionless. So those are your only 2 forces. So this actually looks pretty similar to our example problem. Once we break gravity down into its vectors, Fgx, again, along the incline itself, Fgy is perpendicular to it, and then your normal force is that way. And we rarely ever have to worry about these 2 forces because they cancel each other out, this one and this one, and we're only left with this. So when we ask to calculate F of Gy, that's a pretty easy calculation. It is mg times cosine theta here, and what we have is an incline here of 35 degrees, we're told, and a mass of 100. So if I do 100 times 9.81 times cosine of 35, I get that f of g y is about 803.5 newtons. And technically what I guess the question that was asked to us is not what is FGY, what is the normal force? But what you see is that the normal force and FGY, they have to cancel each other out. So if we did the second law in the y direction, we could actually prove that to ourselves. So let's write F net in the y direction. That does equal 0 because there's no motion in the y direction. It is all in the x direction here. So keep in mind our coordinate system's like this: positive, positive, negative, negative. N is in the positive direction, f of gy is in the negative direction, and then again, once we just move that over there, we get that f, gy, and n are equal to each other. So n must also be 803.5 newtons. So that's one of the things you want to be aware of here, is that you always have the ability to solve for the normal force on the inclined plane. It's always going to be equal to f, gy. And then once you do that, we can take a look at the net force. Knowing that these two cancel out, we're just left with this here. And that's going to be in the x direction exclusively. So if we did F net in the x direction, that is equal to ma. And the only force I see left over, especially the only force in the x direction, is Fgx here. So when I solve for Fgx, I will get the net force here. So F of Gx is equal to mg sine theta. And when I put those numbers in, 100, 9.81, sine of 35, what we should end up getting is 562.7 newtons, approximately. And then what we can do is then solve for the acceleration knowing the numerical value of that. So when we put in our value for m here of 100, our unknown is a, and we have 562.7 newtons here. When we divide both sides by 100, we'll get our acceleration, and that would be 5.627 meters per second squared for our acceleration. So again, a pretty easy problem, not that much math overall, and if you understand what's happening conceptually, this actually comes together a lot quicker. Now the last problem, I shouldn't say last problem, but problem number 5 here, that says let's take this exact same scenario, but let's add a force of kinetic friction into it. So this is actually something that we have to pay attention to the details quite a bit here. So our object is still going to be very similar because we're still going to have f of gx that way, we're still going to have f of gy that way, and we're still going to have our normal force. Now let's not waste time because we actually already determined what these things were. F of gy, we said that that is 803.5 newtons. We said that the normal force is 803.5 newtons. They're both equal to each other. And we said that f of gx is 562.7 newtons. But the one thing that we can't overlook is that we now have a new force in play, and that's our force of kinetic friction because this thing is sliding. So let's call that f of k. And we now need to take a look at that. Think about our old formula for force of kinetic friction. It was F of k equals mu kn, and in this problem we're told that mu k is equal to 0.1, and we already have the value for n. So knowing those two things, we can get our force of kinetic friction here. F of k, we'll just plug in the numbers. It would equal 0.1 times the normal force, which is 803.5. So we're basically using our work from the previous problem to, move quickly through this. And what we get is that there is a force of kinetic friction of 80.35 newtons. And that is in the negative direction as opposed to the positive direction. So now our net force is a little bit more complicated here. We got two forces working against each other here. You got a 562.7 Newton force in the positive direction, and you got an 80.35 Newton force in the negative direction. So we can use the second law to approach this. Let's do it in the x direction, which is this direction right here. The net force in the x direction is equal to ma. And let's look at these two vectors here. That's positive, that's negative. So This is always our opportunity to write out these forces. I'll write f of gx as positive, f of k as negative, and we happen to know the numerical values of both of these. So what we can do is plug in the numbers and get them. That would be 562.7 minus 80.35. So when I do that, I believe I get that this is equal to about 482 newtons. Now we also happen to know the mass here. So our net force is 482 newtons, but now when we divide by the mass of 100, we're going to get our acceleration. And once we've added in friction, we see that it has definitely decreased the acceleration relative to the previous scenario. So we get 4.82 meters per second squared there.